In this last section, we are looking at light as a particle. Now, we've been thinking of light as a wave, specifically as a transverse wave. And the author did spend quite a bit of time going through the electromagnetic spectrum, because really what light as a wave is, because it can travel through a vacuum of space where we'd say there really isn't anything. There's no medium out there for it to travel through, for it to disturb, which is what we said the definition of a wave was. It's a disturbance of a medium as it travels through it. So how can we even consider light as a wave? Well, when light is classified as a wave, really what's oscillating are electronic or electric and magnetic fields are oscillating one another. And if that's hard for you to understand, you're with the vast majority of the population. Most of us don't completely understand it either. But we've just kind of come to accept the fact that sometimes light behaves more as a wave, as you can see through the double slit experiment, which hopefully you watched that video and got a picture of kind of what that entails. But sometimes it's better for us to think of light as a particle. And it's what actually you would think of it as a bundle of waves. And so if we're thinking of light as a wave, we're going to be using this C equals frequency times wavelength, where C is the speed of light. I mean, it looks very much like the other equation we were using, except there was a V over here before. Well, now there's a C because the speed of light in a vacuum is 3.0 times 10 to the 8th meters per second. And so because that's a constant, now remember the speed of sound was not a constant because it depends on temperature. But the speed of light does not depend on temperature, and so it's going to be a constant. So we change up that V for a C when we're talking about light. Now, when light behaves as a particle, we think of it as a bundle, and it is a bundle of energy. And so to use light as a particle, we know that energy, E, is equal to H times F, where H is Planck's constant, and then F is the frequency of the light. Now, where's the situation where we're going to use something like that? If you have a metal and you shine light on that metal, if you have light that is of a sufficient frequency, the electrons can actually break free of the atoms that are in the metal if they've been given enough energy to do so. And so that's actually called the work function. The work function is the amount of energy that's required for an electron to be able to break through or to break off of the atoms in the metal and then to be released. So if you look at example 11.4, it says that sodium metal has a work function of 2.28 electron volts. So what that's saying is that if we can give an electron 2.28 electron volts, it will break free from its atom and go flying off with a piece of metal, okay? So if blue light, which has a wavelength of 4.25 times 10 to the minus 7th meters, is shined on sodium, what is the maximum kinetic energy of the electrons that are emitted from the metal? Okay, so if I'm looking for energy, what's going to happen is that if I would only give it enough energy in the light particles that I'm shining to allow the atom to allow the electron to break off, then I would just be giving it 2.28 electron volts, and it would break off and it would just kind of sit there. But if I'm able to give it a little more energy, it will break off, and then it would have enough energy also to move. So that's why it's talking about kinetic energy there. So in order to figure out what the maximum kinetic energy of the electrons would be, I need to figure out what energy the light has that I'm giving to the metal. Well, in order to calculate the energy that I'm giving to it, I also have to know the frequency. This is a constant, so I always know what this is. So I have to know the frequency. I don't know the frequency, they gave me the wavelength. So where I have to start is by using C equals F times lambda. The speed of light is 3.0 times 10 to the 8th meters per second. I don't know the frequency, that's what I'm trying to find, but they told me that the wavelength is 4.25 times 10 to the minus 7th meters. Now, sometimes you're going to see wavelength of light expressed in nanometers, and 1 nanometer is 1 times 10 to the minus 9th meters. So this would actually be 425 nanometers. This time they gave it to you in meters. Sometimes they will give it to you in nanometers, and you will have to convert it. In this case, we don't have to convert because it's already in meters. So the frequency, when I divide this out, is going to be 7.1 times 10 to the 14th hertz. Okay, two significant figures because I only know speed of light to two significant figures. Okay, so there's the frequency. Now I can calculate the amount of energy that these photons of light have. So energy equals H times F. So Planck's constant is 4.14 times 10 to the minus 15th electron volt seconds. Now electron volt is just a unit of energy. It's kind of like a joule, except when we're talking about photons of light, a joule would be way, way, way too big. An electron volt is much smaller, and so that's why we're using that unit instead. So H times F, I already calculated the frequency was 7.1 times 10 to the 14th, and it would be hertz, which is also per second. If I do it per second, then you can see that this second and this second will cancel out, and so that will give me an energy of 2.9 electron volts. So this is how much energy the photons actually possess. It's 2.9 electron volts. The work function, it told me, was 2.28 electron volts. So now it's possible that the photon of light could hit the electron and it wouldn't give all of the energy to the electron. So what we're doing is we're saying, okay, if it does give all of its energy over to the electron, how much kinetic energy would be the maximum amount that the electron could have? Well, if it has an energy of 2.9 electron volts and it only needed 2.28 electron volts in order to be released from the metal, then all I have to do is subtract those two, and that will tell me how much potential kinetic energy it would have. That probably sounded confusing. It's not potential kinetic energy. What the possible amount of kinetic energy would be. That's really what I was trying to say. So if I subtract those two off, that's going to give me 0.6 electron volts, which would be the maximum amount of kinetic energy that the photon could possibly have. So you'll get some practice working those today.